as a dwarf planet by the International Astronomical Union (IAU), in 2008 solidified its place in scientific literature. One of the most remarkable features of Haumea is its rapid rotation. The dwarf planet completes a full rotation on its axis in approximately 3.9 hours, making it one of the fastest rotating large objects in the solar system. This extreme spin has dramatically influenced Haumea's shape, causing it to become elongated into a triaxial ellipsoid rather than a near-spherical form like many other celestial bodies. Measurements estimate its dimensions to be approximately 2322 by 1704 by 1138 kilometers, highlighting its distorted structure. The cause of Haumea's rapid rotation remains a subject of ongoing investigation. The prevailing hypothesis suggests that Haumea may have experienced a colossal impact early in its history. This collision not only accelerated its spin, but also ejected a significant amount of material into space, potentially forming a family of smaller objects that share similar orbital characteristics. These fragments, known as the Haumea family, consist of icy bodies scattered across the Kuiper belt. Haumea's surface is predominantly covered with crystalline water ice, as revealed by spectral analysis. This icy surface reflects sunlight efficiently, giving Haumea a high albedo of approximately 0.66. The presence of crystalline ice is intriguing, as it typically forms at relatively high temperatures, which contradicts the frigid environment of the Kuiper belt. Scientists hypothesize that tidal heating or past radioactive decay within Haumea may have provided the necessary energy to maintain its surface in a crystalline state. The dwarf planet also exhibits signs of surface heterogeneity, with darker regions potentially composed of organic compounds or rocky material. These features may indicate a complex history of resurfacing events, impacts, and thermal evolution. Haumea is accompanied by two known moons, Hayaka and Namaka, named after the daughters of the Hawaiian goddess. Hayaka, the larger of the two, orbits Haumea at a distance of approximately 49,880 kilometers and has a diameter of about 310 kilometers. Namaka, the smaller moon, has an irregular shape and orbits closer to Haumea. The study of these moons has provided valuable clues about Haumea's formation and the dynamics of its system. The orbital characteristics of Hayaka and Namaka suggest that they may have formed as a result of the same giant impact that influenced Haumea's rapid rotation. Their compositions are also rich in water ice, further supporting the theory that they originated from Haumea's outer layers. In 2017, astronomers made the surprising discovery of a ring around Haumea. This ring, composed of particles, lies in Haumea's equatorial plane and is situated at a distance of about 2,287 kilometers from its center. The presence of a ring around a dwarf planet was unexpected, as such structures are typically associated with gas giants like Saturn. The discovery of Haumea's ring has sparked new discussions about the mechanisms that can lead to the formation of such features in small celestial bodies. Haumea orbits the Sun at an average distance of 43 astronomical units, AU, placing it well within the Kuiper belt, a region populated by icy bodies and remnants from the early solar system. Its orbital period is approximately 283 Earth years, and its path is moderately elliptical, with an eccentricity of 0.19. Haumea's inclination of 28 degrees relative to the ecliptic plane further distinguishes its orbit from other Kuiper belt objects. The Kuiper belt itself is a treasure trove of scientific discoveries, as it contains objects that have remained relatively unchanged since the formation of the solar system. Haumea's unique properties make it a key subject of study for understanding the physical and chemical processes that shaped this distant region. Haumea's rapid rotation, unusual shape, and icy composition challenge traditional models of planetary formation. The study of Haumea and its system offers critical insights into the processes of accretion, differentiation, and impact events in the early solar system. Moreover, Haumea serves as a natural laboratory for studying the interactions between celestial bodies, including tidal forces, collisional dynamics, and the formation of secondary systems such as rings and moons. Additionally, the discovery of Haumea's ring system has expanded our understanding of ring dynamics and their prevalence among different types of celestial objects. By studying Haumea, scientists can refine their models of ring formation and stability, potentially uncovering new mechanisms that operate in the outer solar system. Despite its significance, Haumea remains a relatively unexplored object. No spacecraft have visited this distant dwarf planet, and much of our knowledge comes from ground-based observations and telescopic studies. Future missions to the Kuiper Belt, such as proposed flybys or orbiters, could provide unprecedented data on Haumea's geology, composition, and evolution. Advances in technology, including powerful space telescopes and adaptive optics, are also expected to enhance our understanding of Haumea. These tools will enable astronomers to resolve finer details of its surface, study its ring system in greater depth, and analyze its moons with higher precision. Haumea, with its striking features and mysterious history, stands as a testament to the complexity and diversity of the solar system. Its study not only deepens our knowledge of distant worlds, but also sheds light on the fundamental processes that govern planetary systems. As exploration of the outer solar system continues, Haumea will undoubtedly remain a focal point of scientific curiosity, inspiring new generations of researchers to uncover the secrets of this remarkable dwarf planet. Haumea's rapid rotation and elongated shape raise profound questions about the dynamics of planetary bodies in the outer solar system. One of the most plausible explanations for its current state involves a massive collision with another large Kuiper Belt object, KBO, early in its history. Such an impact would not only have accelerated Haumea's spin, but also caused significant material to be ejected into its surroundings, giving rise to the family of objects now associated with it. These fragments share similar orbital characteristics and spectral features, suggesting a common origin. By studying these fragments, scientists can reconstruct the conditions and events that shaped Haumea, offering a rare glimpse into the violent early stages of planetary formation. The crystalline water ice observed on Haumea's surface is another enigmatic feature. Crystalline ice forms at temperatures above 110 K, which is significantly warmer than the average temperature in the Kuiper Belt, where conditions are typically frigid, with temperatures hovering around 40 K. This discrepancy suggests that Haumea may have undergone internal heating in its past. The source of this heating could have been tidal interactions, radiogenic decay, or even residual heat from the giant impact that shaped its rotation. This internal activity might have led to resurfacing events, exposing fresher ice layers while burying older, darker material beneath the surface. Such processes would explain the varying albedo and composition observed on Haumea today. The discovery of Haumea's ring added an unexpected dimension to its study. Rings around small bodies like Haumea challenge traditional notions of how such features form and persist. Theories suggest that the ring could be the result of collisional debris that never coalesced into a moon or material ejected from Haumea's surface due to its rapid rotation. The particles in the ring are believed to orbit within the Roche limit of Haumea, where tidal forces prevent them from clumping together into a larger body. Detailed analysis of the ring's composition and dynamics could provide valuable clues about the interactions between Haumea's surface and its surrounding environment, as well as the role of centrifugal forces in maintaining the ring structure. Haumea's moons, Hayaka and Namaka, offer additional opportunities to explore the dynamics of this unique system. Hayaka, the larger of the two, is particularly intriguing due to its relatively high albedo and water ice-rich composition, which mirror the surface features of Haumea itself. This similarity supports the hypothesis that Hayaka formed from material ejected during the same collision that shaped Haumea's rapid spin. Namaka, on the other hand, has an irregular orbit that suggests past interactions with Hayaka or tidal effects from Haumea. The study of these moons can reveal much about the long-term evolution of multi-body systems and the gravitational interactions that govern their stability. The Kuiper Belt, where Haumea resides, is a region filled with ancient relics of the solar system's formation. Unlike the inner planets, which have undergone significant geological and atmospheric evolution, Kuiper Belt objects, KBOs, are thought to have remained relatively pristine. Haumea, however, stands out due to its dynamic history and unique features. Its study provides a counterpoint to other KBOs, highlighting the diversity of processes that have shaped this distant region. By comparing Haumea with other large KBOs like Pluto, Eris, and Makemake, scientists can build a more comprehensive picture of the Kuiper Belt's formation and the role of giant impacts in shaping planetary systems. The presence of organic compounds on Haumea's surface is another area of active research. These compounds, often referred to as tholins, are formed through the photochemical reaction of simple molecules like methane and nitrogen under the influence of ultraviolet light and cosmic rays. The detection of tholins on Haumea suggests that complex chemical processes are at work even in the cold, distant reaches of the solar system. These organics may hold clues to the chemical precursors of life, offering insights into the potential for habitability on icy worlds. Future exploration of Haumea could revolutionize our understanding of the outer solar system. While no spacecraft has yet visited this distant world, its study remains a high priority for missions aiming to explore the Kuiper Belt. A dedicated mission to Haumea could include high-resolution imaging, spectroscopy, and in-situ analysis of its ring and moons. Such a mission would provide detailed data on its surface composition, internal structure, and the dynamics of its unique system. Advances in propulsion technology and miniaturized instruments could make such a mission feasible within the next few decades. Observations from Earth-based telescopes and space observatories like the James Webb Space Telescope, JWST, are already helping to refine our understanding of Haumea. High-precision measurements of its light curve, for example, have provided detailed information about its shape and rotation. Spectroscopic studies have revealed subtle variations in its surface composition, hinting at a more complex history than previously thought. These observations underscore the importance of continued investment in astronomical infrastructure to study distant objects like Haumea. Haumea's story is not just about a single dwarf planet, but about the broader processes that govern the evolution of planetary systems. Its rapid rotation, elongated shape, icy surface, and dynamic environment serve as a microcosm of the interplay between impacts, rotation, and gravitational forces. By studying Haumea, scientists are not only uncovering the secrets of a distant world, but also gaining insights into the forces that have shaped the solar system as a whole. As our understanding deepens, Haumea will undoubtedly continue to inspire new theories, discoveries, and explorations in the field of planetary science. The study of Haumea provides a window into the physical processes that shaped not only the Kuiper Belt but also planetary systems beyond our own. Its elongated shape and rapid spin are unique among known celestial objects of its size, creating a natural laboratory to test theories of rotational dynamics, collisional evolution, and the behavior of matter under extreme conditions. When viewed through this lens, Haumea becomes more than just a distant, icy world. It transforms into a cosmic puzzle piece, revealing how primordial material evolves over billions of years. One of the most compelling aspects of Haumea is its ring, an unexpected feature for a body of its size. This ring system challenges traditional planetary science, as rings have historically been associated with massive gas giants like Saturn, Jupiter, Uranus, and Neptune. The discovery of Haumea's ring suggests that such features may be more common than previously thought, particularly in the Kuiper Belt. The ring's stability and persistence imply that Haumea's rapid rotation plays a central role in maintaining this structure. Centrifugal forces generated by its spin likely prevent the material in the ring from coalescing into a moon or falling back to the planet's surface. Detailed studies of Haumea's ring dynamics could also shed light on the broader phenomenon of ring formation across the solar system. For instance, scientists are interested in whether the particles in Haumea's ring have a consistent size distribution or whether they vary significantly. Understanding these details might help researchers model the processes that lead to the formation of rings and predict where they might be found around other celestial bodies. Spectroscopic observations of Haumea have revealed the presence of minerals and compounds that hint at its internal composition. While the surface is predominantly crystalline water ice, there are also indications of silicates and other rocky material. This dual nature suggests that Haumea underwent a process of differentiation early in its history, with denser materials sinking to form a rocky core while lighter, volatile-rich materials migrated to the surface. Such differentiation processes are critical for understanding how planetary bodies evolve from homogeneous mixtures of material into layered structures with distinct geological and chemical properties. The presence of crystalline water ice on Haumea is particularly intriguing because it implies relatively recent geological activity. In the frigid temperatures of the Kuiper Belt, crystalline ice would ordinarily transition to an amorphous state over time due to cosmic ray bombardment and the natural degradation of its molecular structure. The persistence of crystalline ice on Haumea suggests that the dwarf planet may have undergone resurfacing events in its geologically recent past. These could have been triggered by tidal heating from its moons, internal radioactive decay, or even impacts from other Kuiper Belt objects. Each of these scenarios carries implications for the thermal and mechanical evolution of icy bodies in the outer solar system. Another fascinating area of research is the role of Haumea's moons, Haumea and Namaka, in shaping its dynamical environment. The larger moon, Haumea, appears to be rich in water ice, which aligns with the spectral properties of Haumea itself. This suggests that Haumea may have formed from material ejected during the giant impact that gave Haumea its rapid rotation. Namaka, the smaller and more irregularly shaped moon, exhibits a more chaotic orbit, likely influenced by gravitational interactions with both Haumea and Haumea. The complex orbital dance between these three bodies provides a natural laboratory for studying tidal forces, orbital resonance, and the long-term stability of multi-body systems. The detection of organic compounds, or tholins, on Haumea's surface also opens the door to exciting possibilities in astrobiology. Tholins are complex organic molecules that form when simpler compounds, such as methane and nitrogen, are exposed to ultraviolet radiation and cosmic rays. These molecules are believed to be precursors to the building blocks of life, such as amino acids and nucleotides. While Haumea's harsh surface environment is unlikely to support life as we know it, the presence of tholins raises questions about the chemical evolution of organic materials in the outer solar system. It also suggests that similar processes could occur on other icy worlds, such as Europa, Enceladus, or Titan, which are considered potential habitats for microbial life. Further exploration of Haumea could yield transformative insights into these scientific questions. A mission to Haumea would likely include a suite of advanced instruments, such as high-resolution cameras, spectrometers, and magnetometers, designed to study its surface, interior, and surrounding environment. Flyby missions, similar to NASA's New Horizons encounter with Pluto, could map Haumea's surface features, analyze its composition, and measure the properties of its ring and moons. A more ambitious mission might involve an orbiter, which could spend months or even years collecting detailed data on Haumea's geology, magnetosphere, and thermal properties. The potential for comparative planetology is another compelling reason to study Haumea. By comparing Haumea with other dwarf planets like Pluto, Eris, and Makemake, scientists can develop a broader understanding of the processes that shape icy worlds in the Kuiper Belt. For example, while Pluto and Eris are characterized by their large atmospheres and complex surface chemistry, Haumea's unique features, its rapid spin, elongated shape, and ring system, offer a complementary perspective on the diversity of planetary evolution in this region. Haumea's study also has implications for exoplanet research. Many exoplanets discovered in distant star systems are thought to be icy or rocky bodies similar in size and composition to the Kuiper Belt's largest objects. By understanding the physical and chemical properties of Haumea, scientists can refine their models of exoplanet formation and behavior, particularly for planets located in the colder, outer regions of their star systems. Haumea thus serves as both a window into our own solar system's past and a guide for exploring planetary systems beyond. In addition to its scientific importance, Haumea captivates the imagination of the public and inspires a sense of wonder about the outer reaches of the solar system. Its elongated shape, shimmering icy surface, and mysterious ring evoke the kind of curiosity that has always driven human exploration. As scientists continue to unravel its secrets, Haumea reminds us of the boundless mysteries that await discovery in the vast expanse of space. Through its study, we deepen not only our understanding of the cosmos but also our appreciation for the complexity and beauty of the universe. Haumea stands as a testament to the intricate interplay of forces that have shaped our solar system over billions of years. Its rapid rotation, dynamic system of moons, and enigmatic surface composition challenge traditional models of planetary science, while opening new avenues for exploration and discovery. In studying Haumea, scientists are not merely piecing together the history of a single dwarf planet. They are uncovering the fundamental principles that govern the evolution of worlds, both within our solar system and beyond. Haumea's extraordinary features draw astronomers deeper into the mysteries of planetary science, serving as a gateway to understanding not just the outer solar system, but the very forces that shaped the universe. Its rapid spin, peculiar shape, and unexpectedly complex system challenge long-held theories and invite tantalizing questions about how such a unique object could have formed and evolved. Theories surrounding Haumea's creation are among the most debated in modern astronomy. One compelling hypothesis suggests that Haumea may have been part of a much larger protoplanet, which collided with another massive object early in the history of the solar system. The violence of this impact likely stripped away a significant portion of Haumea's mass, leaving behind the elongated, rapidly spinning body we see today. The debris from this event is thought to have coalesced into its moons, Hyakka and Namaka, and the family of icy fragments scattered throughout the Kuiper Belt. This idea not only explains Haumea's rapid rotation but also aligns with observations of other collisional families within the belt. The high albedo of Haumea, driven by its crystalline water-ice surface, raises intriguing questions about its thermal history. Crystalline ice, as opposed to amorphous ice, requires a heat source to maintain its structure. Yet the Kuiper Belt is one of the coldest regions in the solar system, making the persistence of such ice an anomaly. Could Haumea's interior still retain enough heat to periodically resurface its icy crust? If so, this would imply ongoing geological processes in a region once thought to be geologically dead. One possibility is that radioactive isotopes deep within Haumea's rocky core could provide a steady source of internal heat. Even trace amounts of isotopes like potassium-40, uranium-238, or thorium-232 could sustain low-level heating over billions of years, enough to influence the planet's surface over geological timescales. Alternatively, tidal interactions with its moons might generate localized heating, particularly if Hyakka and Namaka once orbited much closer to Haumea. These interactions could create frictional forces within Haumea's interior, resulting in periodic episodes of melting and resurfacing. Adding to the intrigue, Haumea's ring presents a scientific enigma that has reshaped how astronomers think about small planetary bodies. Observations suggest the ring is made of icy particles that orbit in a remarkably stable configuration. This stability is surprising given Haumea's rapid rotation and elongated shape, both of which create complex gravitational forces. Models of the ring's dynamics indicate that it likely formed from material ejected from Haumea's surface, possibly during a past collision or through ongoing sublimation processes. The fact that the ring orbits close to Haumea's equatorial plane hints at a strong coupling between the planet's spin and the distribution of material around it. What makes Haumea's ring even more fascinating is its interaction with the planet's gravity field. Haumea's elongated shape creates an uneven gravitational potential, meaning that objects orbiting close to its surface experience varying degrees of pull depending on their position. This creates a dynamic environment where particles in the ring must maintain a delicate balance to avoid being flung outward or drawn inward. Studying this system offers new insights into how similar processes might occur around other small, rapidly rotating objects, both within and beyond our solar system. Moving beyond Haumea itself, the implications of its existence ripple through the field of planetary science. The Kuiper Belt, once thought to be a relatively quiet and uneventful region, is now seen as a hotbed of complex interactions. Haumea, along with other large Kuiper Belt objects like Eris, Makemake, and Quaoar, reveals that this region is anything but static. Collisions, migrations, and even the formation of moon systems are ongoing processes, reshaping our understanding of the outer solar system. Haumea's discovery and classification as a dwarf planet also underscore the dynamic and evolving nature of astronomy. When Pluto was reclassified in 2006, it sparked a reevaluation of what constitutes a planet. Haumea's unique characteristics, its irregular shape, rapid rotation, and ring system, have expanded the conversation further, challenging scientists to refine their definitions and consider the incredible diversity of planetary bodies. One of the most tantalizing aspects of Haumea is its potential connection to other planetary systems. Astronomers have discovered thousands of exoplanets orbiting stars beyond our Sun, many of which are icy or rocky bodies similar in size and composition to Haumea. The processes that shaped Haumea, collisions, spin dynamics, and gravitational interactions, are likely at play in these distant systems as well. By studying Haumea, scientists can test models that may apply to planets forming around other stars, bridging the gap between our solar system and the broader galaxy. Advances in observational technology promise to revolutionize our understanding of Haumea in the coming decades. The James Webb Space Telescope, JWST, and next-generation ground-based observatories like the Extremely Large Telescope ELT, will be capable of resolving finer details of Haumea's surface and ring system. These instruments will provide high-resolution spectra, revealing the precise chemical makeup of Haumea's ice and any organic compounds present. Such data could illuminate the role of complex chemistry in shaping the outer solar system, offering clues to the origins of life's building blocks. The possibility of a dedicated mission to Haumea also looms on the horizon. Such a mission could deploy state-of-the-art instruments to probe Haumea's internal structure, study its moons in detail, and capture close-up images of its surface and ring. In situ sampling of ring particles could provide direct evidence of their origin, while radar imaging could reveal hidden subsurface features. These efforts would not only enhance our understanding of Haumea, but also set the stage for exploring other distant, icy worlds. Perhaps the greatest mystery of Haumea is its ability to continuously surprise and challenge our understanding of the cosmos. Every new discovery, be it its moons, ring system, or peculiar shape, adds another layer of complexity to a body that defies simple categorization. Haumea is a reminder that the universe is full of wonders waiting to be uncovered, and that even the most distant and inaccessible objects can hold the key to profound scientific revelations. Its study is not just a journey to the edges of our solar system, but a quest to understand the forces that shape all planetary systems, including our own. Haumea's mysteries continue to captivate scientists, as each new observation seems to pose more questions than answers. Its existence as a fast-spinning, elongated dwarf planet challenges conventional models of planetary formation, particularly in the context of the Kuiper Belt. Most celestial bodies in this region are thought to have formed through the gradual accretion of smaller objects over millions of years. However, Haumea's unique characteristics suggest that its story is far more dramatic, involving catastrophic collisions, rapid evolutionary processes, and interactions with its surrounding environment that set it apart from its neighbors. One of the most exciting areas of ongoing research is the study of Haumea's internal structure. Based on its shape, density, and rotational speed, scientists believe that Haumea has a differentiated interior, with a dense rocky core surrounded by a thick mantle of water ice. This layered structure implies that Haumea once generated enough heat to allow heavy materials to sink to its center while lighter materials floated to the surface. The source of this heat remains a subject of debate. While radioactive decay within its core could explain some of the energy, it is also possible that the massive impact theorized to have shaped Haumea contributed a significant amount of heat, melting large portions of its interior. This differentiation has significant implications for Haumea's long-term evolution. A rocky core surrounded by an icy mantle would create a natural boundary where heat transfer occurs, driving processes like convection or even cryovolcanism. Cryovolcanism, or cold volcanism, involves the eruption of water, ammonia, or other volatile substances instead of molten rock. On Haumea, cryovolcanism could periodically refresh its surface, bringing fresh crystalline ice to the surface and explaining its high albedo. Such processes have been observed on other icy bodies, like Saturn's moon Enceladus, and their potential existence on Haumea raises fascinating questions about geological activity in the frigid reaches of the Kuiper Belt. Haumea's rapid rotation plays a crucial role in shaping its unique characteristics. Spinning at such an extraordinary speed, completing a full rotation every 3.9 hours, Haumea experiences intense centrifugal forces that distort its shape into a triaxial ellipsoid. This shape, combined with its density of approximately 2.6 g/cm superscript 3, suggests a composition that is denser than pure ice but less dense than a fully rocky body. These centrifugal forces may also affect the distribution of material within Haumea, potentially creating subsurface stresses and fractures. Such stresses could allow volatile substances trapped beneath the surface to escape, further contributing to surface renewal. Haumea's moons, Hayaka and Namaka, are key players in understanding its history and dynamics. Hayaka, the larger and more distant of the two, orbits Haumea in a nearly circular path and has a surface rich in water ice. This moon's composition and orbit suggest that it likely formed from material ejected during the hypothesized giant impact that shaped Haumea. Namaka, the smaller and closer moon, exhibits a more eccentric and irregular orbit, hinting at a complex gravitational interplay with Haumea and Hayaka. Over time, these interactions could have caused tidal heating within Haumea, potentially driving internal processes like the movement of ice and rock or the release of gases from the interior. The discovery of Haumea's ring added yet another layer of intrigue to this already extraordinary dwarf planet. Rings are typically associated with massive gas giants, where strong gravitational fields and complex orbital dynamics create stable environments for ring systems. The existence of a ring around Haumea suggests that even small, rapidly spinning bodies can maintain such structures under the right conditions. Observations indicate that Haumea's ring lies close to the planet's Roche limit, the distance within which tidal forces prevent particles from coalescing into a larger body. The particles in Haumea's ring are thought to be composed of water ice, and their size and distribution provide valuable clues about the processes that sustain the ring. Understanding the origin of Haumea's ring system requires considering its violent past. One possibility is that the ring formed from debris created by a collision with another Kuiper belt object. Such an impact could have ejected material into Haumea's orbit, where it gradually settled into a stable ring. Another theory posits that the ring is made up of material that was ejected from Haumea's surface due to centrifugal forces caused by its rapid rotation. This would imply a continuous interaction between Haumea's surface and its surrounding environment, with material constantly being added to the ring. Haumea's composition, surface features, and moons are not the only elements that make it scientifically fascinating. Its orbit within the Kuiper belt offers a glimpse into the dynamics of this distant region of the solar system. The Kuiper belt is home to a wide variety of objects, ranging from small, icy bodies to larger dwarf planets like Pluto and Eris. These objects are remnants from the early solar system, preserved in a state that reflects the conditions of their formation. Haumea, however, stands out as an active participant in the ongoing evolution of this region. Its rapid rotation, dynamic moon system, and ring highlight the complex interactions that continue to shape the Kuiper belt. The broader implications of Haumea's study extend to our understanding of planetary systems beyond the solar system. Exoplanets discovered in distant star systems often display characteristics similar to those of Kuiper belt objects, including icy compositions and orbits in the colder, outer regions of their systems. By studying Haumea, scientists can refine models of planetary formation and evolution that may apply to these distant worlds. Haumea serves as a natural laboratory for testing theories about the behavior of ice, rock, and volatile materials under extreme conditions. As technology advances, the opportunities to explore Haumea in greater detail grow more promising. Space telescopes equipped with advanced imaging and spectroscopy capabilities could resolve finer details of Haumea's surface and ring system, revealing its chemical composition and geological history. A dedicated spacecraft mission could go even further, capturing high-resolution images, mapping its gravity field, and even sampling particles from its ring. Such a mission would provide an unprecedented look at one of the most unique objects in the solar system, offering answers to questions that continue to challenge our understanding of planetary science. Haumea's story is far from complete. Each new discovery adds a layer of complexity to our understanding of this enigmatic world, reminding us that the solar system is full of surprises. Haumea's rapid rotation, elongated shape, icy surface, and dynamic system of moons and rings make it a scientific treasure trove, offering insights into the processes that have shaped not only our corner of the galaxy, but also the broader universe. As scientists continue to study Haumea, they are not just exploring a distant dwarf planet. They are unlocking the secrets of how worlds form, evolve, and interact on a cosmic scale. Haumea is a mystery wrapped in ice, spinning relentlessly in the frozen abyss of the Kuiper Belt. It defies expectations, a celestial enigma that refuses to fit neatly into the categories of planetary science. Every observation deepens the intrigue, leaving astronomers grappling with questions that stretch the boundaries of our understanding. What ancient cosmic drama sculpted this oblong, crystalline world, and what secrets lie hidden beneath its shimmering, icy surface? Imagine a collision so cataclysmic that it didn't just shatter a primordial world but reshaped it entirely, sending fragments spiraling into the void. Haumea is the survivor of such an event, its rapid spin a scar from the unimaginable force of the impact. This is no ordinary collision victim. Haumea carries the hallmarks of an active and dynamic history, a history that may still be unfolding in ways we are only beginning to glimpse. Its crystalline water-ice surface gleams with an unnatural brightness, a mirror to the sun's faint light that shouldn't exist in a place this cold. How is this possible? Crystalline ice should have long since degraded into a dull, amorphous state under the unrelenting bombardment of cosmic radiation. The surface, scientists suspect, may be alive, renewed by mysterious processes deep within the dwarf planet's interior. Could there still be enough warmth in Haumea to stir its icy mantle, bringing fresh material to the surface? If so, Haumea isn't just an icy relic. It's a world in motion, defying the stillness expected of its kind. And then there's the ring. A perfect circle of icy particles orbits Haumea like a frozen halo, a feature astronomers never anticipated around such a small object. Where did it come from? Was it born in the same violent impact that shaped Haumea itself? Or is it a product of its incredible spin, flinging debris into space? The ring seems impossibly stable, as if tethered by invisible forces we have yet to understand. Studying it could unlock secrets about not just Haumea but every planetary ring in the solar system and beyond. Adding to this celestial puzzle are Haumea's moons, Hayaka and Namaka. They aren't merely companions. They're witnesses to the dwarf planet's turbulent history. Hayaka, with its icy surface and steady orbit, seems to whisper of a time when material was torn from Haumea and coalesced into a satellite. Namaka, in contrast, dances erratically, its irregular orbit hinting at ancient gravitational battles. What stories do these moons hold about their enigmatic host? And what of the mysterious organic compounds suspected to coat parts of Haumea's surface? Tholins, complex molecules forged in the harsh interplay of ultraviolet light and cosmic rays, could be present. These are the building blocks of life, scattered across the most hostile environments. Could Haumea, in its distant isolation, hold clues to the chemistry that led to life on Earth? Or even point toward what might be possible in alien star systems? The intrigue deepens when we consider Haumea's role in the broader narrative of the Kuiper Belt. It isn't alone. Scattered around it are fragments, icy, rocky bodies that seem to have been born from Haumea's destruction. They form a family, orbiting the sun in similar paths, a cosmic fingerprint of the cataclysm that reshaped this corner of the solar system. Studying these fragments is like piecing together a shattered vase. Each piece tells part of the story, but the full picture remains elusive. Haumea isn't just a dwarf planet. It's a challenge. It defies the rules of celestial mechanics, pushes the limits of our understanding of icy worlds, and holds tantalizing clues about the forces that shaped not only the solar system but perhaps countless others. Its ring beckons like a frozen whisper from the void, its spin a dizzying testament to the violence of its past, and its surface a shimmering question mark for astronomers. But the most tantalizing question of all may be this: what if Haumea is just the beginning? What if the Kuiper Belt, with its thousands of icy worlds, holds even stranger secrets? Haumea is a gateway to the unknown, a world that demands exploration. And as we uncover its mysteries, we might find answers to questions we haven't even thought to ask yet. The allure of Haumea lies not just in its icy surface or its rapid spin, but in the secrets it seems determined to keep. As telescopes capture faint glimpses of its distant, distorted form, scientists are haunted by questions that seem almost taunting. Why does Haumea spin so quickly, almost to the brink of tearing itself apart? What ancient forces flung it into this perpetual dance? And could its fate be a warning about the fragility of other celestial bodies? Its ring, hauntingly perfect, defies the odds. Unlike Saturn's grand displays or Neptune's faint arcs, Haumea's ring feels personal, almost intimate, a frozen echo of something violent yet beautiful. Could it be the remnants of an ancient moon, shattered and drawn into the dwarf planet's orbit? Or is it debris continually being shed by Haumea itself, a visible trace of the centrifugal forces working against its icy crust? As astronomers map the ring's structure, they confront the possibility that Haumea is actively reshaping its surroundings even now, creating a dynamic system in one of the solar system's coldest, most distant regions. The deeper mystery lies within. Haumea's elongated shape hints at immense pressures and forces locked in its interior. Imagine a rocky core cloaked in a vast, frozen mantle, where the boundary between rock and ice may not be as static as it seems. Could heat from radioactive decay still linger deep within, creating pockets of liquid water or slush? And if so, what strange, alien chemistry might be taking place in those hidden depths? While the odds of life as we know it are slim, the possibility of complex prebiotic chemistry cannot be dismissed. In a universe where life has arisen once, even the faintest hint of chemical complexity carries profound implications. The moons Hyaka and Namaka orbit Haumea like silent sentinels, their trajectories whispering of gravitational battles fought long ago. Hyaka, with its icy sheen, is a nearly perfect reflection of Haumea's surface, suggesting it was born from the same material. Namaka, more erratic in its orbit, could hold the scars of an orbital resonance that no longer exists, a relic of the chaotic early days of Haumea's formation. Studying their motions is like decoding a forgotten language, where every gravitational quirk and orbital anomaly hints at the violent story of Haumea's creation. And then there's the family, dozens of icy fragments scattered throughout the Kuiper Belt that share Haumea's spectral signature. These fragments are more than debris. They are clues, pieces of a celestial puzzle that astronomers are racing to solve. Why do these objects orbit in similar paths? And why do they all bear the unmistakable mark of water ice? Could these fragments have once formed a much larger body, now lost to time? Or are they evidence of a cosmic chain reaction, a series of collisions that set the stage for the Kuiper Belt as we know it? Haumea also forces us to confront broader, more unsettling questions about the solar system. How many other dwarf planets and small celestial bodies have stories just as dramatic, hidden in the cold darkness beyond Neptune? Are there even stranger worlds waiting to be discovered, with rings, moons, or features we can't yet imagine? Haumea is a reminder that the solar system is far more complex and dynamic than we once thought. A realm of endless surprises that challenges our assumptions about how planets, moons, and rings form and evolve. The potential for exploration looms large. Imagine a spacecraft arriving at Haumea, its cameras capturing the glint of sunlight off its icy surface, and its instruments probing the chemistry of its ring. A close flyby could reveal cracks and fissures in its surface, places where internal processes might have exposed ancient material. Sampling particles from its ring could uncover their origin, fragments of Haumea's crust or relics of an ancient impact. Such a mission would not just answer lingering questions about Haumea, it would redefine our understanding of icy worlds across the galaxy. And yet, Haumea's mysteries feel like they are only deepening. The more we learn, the more questions emerge, as if the dwarf planet itself resists easy categorization. It exists on the edge of the solar system of stability and of what we think is possible for a small icy world. Haumea is not merely a passive remnant of the past, but an active, evolving body that defies expectations at every turn. The ultimate intrigue lies in the unknown. What if Haumea's rapid spin eventually reaches a breaking point? Could it shed more material, creating new moons, or even expanding its ring? What if its interior harbors reservoirs of liquid water, heated by processes we have yet to uncover? And what if its family of fragments is just the beginning, a clue to even larger events that have shaped the outer solar system? Haumea is more than a dwarf planet. It's a story of creation, destruction, and persistence. Its icy surface, shimmering in the distant sunlight, seems almost to beckon, inviting us to uncover its secrets. And as we peer deeper into the Kuiper Belt, searching for answers, Haumea reminds us that the universe is vast, mysterious, and infinitely surprising. The enigma of Haumea is a siren call for explorers of the cosmos. It spins, defying the quiet vastness of the Kuiper Belt, its elongated form and glimmering ice a testament to the chaos of its creation. But what if the story of Haumea is not yet finished? What if this distant dwarf planet, seemingly frozen in time, holds the potential for future cosmic drama? Consider its rapid rotation, an extraordinary feature that may eventually push Haumea to its structural limits. While it has endured for billions of years, the centrifugal forces acting on its surface create immense tension. Could there come a day when a piece of Haumea breaks free, flung into space by the sheer velocity of its spin? Such an event would not only add new fragments to the Haumea family, but also alter the dynamics of its ring and moons, reshaping its system in ways we can only theorize. The interaction between Haumea and its ring is another frontier of intrigue. The ring's stability suggests a finely tuned balance, yet its precise origin remains elusive. Are the icy particles a constant reminder of Haumea's violent past, or do they represent an ongoing process, a steady shedding of material as the dwarf planet spins? If the latter is true, Haumea may be in a perpetual state of renewal, its ring evolving over time in response to the gravitational influences of its moons and its own spin. Future observations may reveal whether Haumea's ring is static or dynamic, offering insights into the forces at play in this icy ballet. Haumea's moons, Hyaka and Namaka, are more than mere satellites. They are the keepers of its secrets. Haumea, with its bright icy surface, seems almost serene, orbiting at a distance that allows it to remain largely untouched by the gravitational tug-of-war closer to Haumea. Namaka, on the other hand, is chaotic, its orbit a reflection of ancient disturbances. Could Namaka's erratic behavior hold the key to understanding the early interactions that shaped Haumea's system? Perhaps its gravitational dance with Haumea and Haumea is still unfolding, creating subtle shifts that ripple across the entire system. But the greatest mysteries may lie beneath Haumea's icy crust. While its surface dazzles with crystalline ice, its interior could harbor layers of untapped potential. Imagine a hidden ocean, warmed by the residual heat of radioactive decay or the friction of tidal forces. Such an ocean, buried beneath kilometers of ice, would be an isolated world, untouched by sunlight yet teeming with chemical potential. Could it contain the building blocks of life, locked away in the cold depths of this distant dwarf planet? While direct exploration of Haumea's interior remains a distant dream, its study could inspire future missions to icy moons and planets across the solar system. Haumea's orbit through the Kuiper Belt is another piece of the puzzle. Its inclination and eccentricity suggest a tumultuous past, possibly shaped by interactions with Neptune or other massive bodies in the outer solar system. Such gravitational encounters could have influenced not only Haumea's orbit but also its spin and the distribution of its family of fragments. By tracing the orbital histories of Haumea and its kin, scientists hope to reconstruct the events that led to its current state. In doing so, they may uncover new clues about the broader dynamics of the Kuiper Belt and the role of giant planets in shaping its structure. The implications of Haumea's study extend beyond the Kuiper Belt. As astronomers discover more exoplanets, they are finding worlds that mirror the characteristics of Haumea: icy, fast-spinning, and orbiting far from their parent stars. By unraveling the mysteries of Haumea, we gain a template for understanding these distant worlds, many of which may be too far away for direct observation. Haumea, in this sense, is a bridge between our solar system and the wider galaxy, offering a glimpse into the universal processes that shape planetary bodies. The story of Haumea is a reminder that the cosmos is full of surprises. Its existence challenges assumptions, pushing scientists to rethink what is possible in the outer solar system. It is a testament to the resilience of planetary bodies, enduring billions of years of gravitational forces, impacts, and cosmic radiation, all while maintaining its dynamic, enigmatic character. As humanity's reach into space extends further, Haumea beckons as a target for future exploration. A mission to this icy world could answer questions that have eluded us for decades. What is the precise composition of its ring? How do its moons interact with each other and with Haumea? And perhaps most tantalizingly, what lies beneath its surface? A spacecraft could orbit Haumea, mapping its gravitational field, analyzing its surface composition, and even capturing high-resolution images of its moons and ring. Such a mission would not only illuminate Haumea's mysteries, but also pave the way for exploring other icy worlds, from the Kuiper Belt to exoplanetary systems. Until then, Haumea spins on, its secrets intact, daring us to look closer. It is a reminder of the beauty and complexity of the universe, a beacon in the darkness of the Kuiper Belt that challenges us, a distant dwarf planet. It's a storyteller. Its every characteristic, from its dizzying rotation to its icy ring, seems to whisper fragments of a narrative that stretches back to the birth of the solar system. But these fragments are incomplete, like pages torn from an ancient book. To piece them together, we must look beyond what we know, daring to imagine the unimaginable. What if Haumea isn't just the product of a single cataclysmic event, but a survivor of multiple cosmic dramas? Each twist of its elongated form, each icy fragment in its ring, may tell of eons of impacts, gravitational disruptions, and tidal forces that molded it into the object we see today. Its rapid spin, an anomaly in itself, raises the question: how much longer can Haumea endure this relentless pace? The centrifugal forces at work threaten to stretch it to its limits, hinting that this story is far from over. Could Haumea still be in the process of transforming, shedding pieces of itself into the void, slowly altering its shape and structure as it dances through space? Then there's the haunting possibility of what lies beneath its icy crust. In the freezing darkness of the Kuiper Belt, where sunlight is a mere whisper, Haumea could harbor secrets beneath its surface. Layers of ice could insulate a hidden world, perhaps a subsurface ocean kept liquid by internal heat. Such oceans have been theorized or discovered on moons like Europa and Enceladus, but on Haumea the stakes feel even higher. Could such an ocean, locked beneath kilometers of ice, hold the chemical precursors of life? Could it serve as a template for understanding the potential habitability of icy exoplanets orbiting distant stars? Haumea's ring adds another layer of intrigue. Its very existence challenges the understanding of where and how ring systems can form. Unlike the majestic rings of Saturn or the subtle arcs of Neptune, Haumea's ring is a stark, icy reminder of a celestial process we've barely begun to comprehend. Every particle in that ring is a messenger from the past, perhaps a fragment of Haumea itself or a relic of an ancient collision. Studying the ring's composition, motion, and interaction with Haumea's gravity will not only unravel its origins, but could reveal new principles of celestial mechanics that apply to planets and moons across the universe. And what of Haumea's family? These icy siblings scattered across the Kuiper Belt are like echoes of the dwarf planet's violent past. They orbit the sun in similar paths, carrying with them the spectral signature of Haumea's icy surface. Together, they form a cosmic breadcrumb trail, leading us back to the moments of collision and chaos that birthed them. By studying these fragments, scientists can reconstruct Haumea's history, piece by piece, gaining insights into the broader dynamics of the Kuiper Belt and the violent forces that shaped our solar system. But perhaps the greatest intrigue lies in Haumea's potential to surprise us. The more we study it, the more it defies easy classification. Is it merely a relic of the past, or is it a dynamic, evolving world? Could it, against all odds, be active today, its surface reshaping itself in slow, deliberate ways, its ring and moons bearing witness to ongoing interactions? Haumea's rapid spin, its shimmering ice, its chaotic moons, they all hint at a story still unfolding, a mystery waiting to be unraveled by the next generation of explorers. Haumea invites us to dream. It challenges us to look beyond the obvious, to question what we think we know about planets, moons, and the forces that govern them. It's a world that reminds us of the fragility and resilience of celestial bodies, of the delicate balance between destruction and creation. And as we gaze at this distant, icy world, spinning on the edge of the solar system, we can't help but wonder, what will we discover next? The universe is vast, and Haumea is just one of its many riddles, a beacon that draws us ever closer to the truth hidden in the stars. Haumea, a distant world sculpted by forces beyond comprehension, stands as a silent witness to the violent and creative processes that have shaped the universe. Its story is not one of mere existence, but of resilience, transformation, and the cosmic ballet that links every particle of the solar system. As we peer into the depths of the Kuiper Belt, Haumea's elongated, icy body emerges as a testament to the unrelenting forces that govern celestial mechanics, a masterpiece born from chaos. Haumea's rapid rotation is an enigma wrapped in physical impossibility. It spins so quickly, once every 3.9 hours, that its form stretches into a triaxial ellipsoid, an egg-shaped defiance of gravity's preference for spherical symmetry. This rate of rotation is far beyond what we observe in most celestial bodies of similar size, raising tantalizing questions. How did Haumea reach such a velocity without tearing itself apart? The leading theory suggests a catastrophic impact with another Kuiper Belt object billions of years ago, a collision so violent that it sent debris scattering into space while spinning Haumea like a cosmic top. Yet, this explanation only scratches the surface. Could there have been multiple collisions? What other unknown forces might have contributed to this relentless spin? This rapid rotation doesn't just shape Haumea's form. It governs its entire system. The centrifugal force at work distorts its gravitational field, creating a unique dynamic environment for its ring and moons. Haumea's ring, an impossibly stable structure of icy particles, orbits close to its equatorial plane, held in place by the delicate balance of gravitational and rotational forces. How such a structure remains intact over billions of years is a puzzle in itself. Did the ring form immediately after the catastrophic impact that birthed Haumea's spin? Or is it the result of ongoing processes? Perhaps material being ejected from Haumea's surface due to its rotational velocity? Every particle in that ring holds a clue, and understanding its origins could unlock secrets not just about Haumea, but about the formation of rings around planets and moons throughout the cosmos. The moons, Haumea and Namaka, add further complexity to this dynamic system. Haumea, the larger moon, orbits Haumea at a distance of nearly 50,000 kilometers, its icy surface reflecting sunlight like a distant echo of Haumea itself. Namaka, closer and more chaotic, moves in an irregular orbit, as if haunted by gravitational disturbances from its sibling and Haumea. These moons are not mere companions. They are key players in the story of Haumea's formation and evolution. The interplay of their orbits reveals a history of tidal forces and orbital resonances, a gravitational tug-of-war that may still be unfolding today. Studying their trajectories and compositions is like reading the final chapters of a book, knowing that earlier pages hold the answers to questions yet unresolved. Beneath Haumea's shimmering surface lies another mystery. Spectroscopic analysis reveals that its icy crust is crystalline, a structure that should not exist in the cold vacuum of the Kuiper Belt. Over time, cosmic radiation would degrade crystalline ice into a dull, amorphous state. Yet Haumea gleams with brilliance, suggesting a surface that is constantly renewed. What drives this renewal? Internal heating from radioactive decay within Haumea's rocky core could be one explanation. Alternatively, tidal interactions with its moons might generate enough friction to melt subsurface ice, driving eruptions of water or slush to the surface in a process akin to cryovolcanism. Such resurfacing would periodically expose fresh ice, explaining its youthful appearance. If this is true, Haumea is not just a relic of the past. It is an active world, quietly evolving in the cold isolation of the Kuiper Belt. The possibility of subsurface oceans beneath Haumea's icy crust elevates its intrigue to another level. These oceans, if they exist, would be insulated from the frigid environment by kilometers of ice, creating a stable environment for complex chemical processes. Could these hidden seas harbor the building blocks of life? On Earth, Life thrives in the unlikeliest of places. Deep-sea hydrothermal vents, subglacial lakes, and extreme environments where sunlight never penetrates. If similar conditions exist on Haumea, even the faintest signs of organic chemistry could redefine our understanding of habitability in the universe. Haumea's story is inseparable from the broader narrative of the Kuiper Belt, a vast and enigmatic region filled with icy bodies that hold the keys to the early solar system. The discovery of Haumea's family of fragments, icy objects that share its orbital path and spectral properties, suggests a violent origin. These fragments are not random. They are pieces of a cosmic puzzle, scattered remnants of a once larger body that was torn apart by unimaginable forces. Studying these fragments provides a window into the conditions of the Kuiper Belt during its formative years, revealing the scale and frequency of collisions that shaped this distant frontier. The Kuiper Belt itself is a realm of wonders waiting to be discovered. Beyond Haumea lie countless other worlds, each with its own story. Dwarf planets like Eris, Makemake, and Quawar challenge our definitions of planetary bodies, offering glimpses into the diversity of the solar system's outer reaches. Haumea stands out among them, not just for its unique shape and spin, but for the sheer number of unanswered questions it poses. It is a reminder that even in the cold, dark outskirts of the solar system, there is activity, evolution, and complexity beyond our wildest imaginings. And then there is the ultimate question: what does Haumea mean for our place in the cosmos? As we discover exoplanets in other star systems, many of them icy, fast-spinning worlds, Haumea serves as a template for understanding the forces at play on distant planets. By studying Haumea, we are not just learning about our own solar system, we are building the tools to explore and understand the galaxy. Haumea is not merely an object of scientific study, it is an invitation to wonder. Its secrets are buried beneath layers of ice and veiled in the complexities of its motion, composition, and history. But these secrets will not remain hidden forever. As our technology advances, as we send spacecraft to the outer reaches of the solar system, we edge closer to uncovering the full story of this remarkable world. Until then, Haumea spins on, a glittering enigma on the edge of the solar system, challenging us to look deeper, to dream bigger, and to never stop seeking the unknown. Haumea continues to orbit the sun as both a tantalizing mystery and a bold reminder of the dynamic, chaotic forces that shaped the early solar system. But this icy world, seemingly isolated in the vastness of the Kuiper Belt, is far from static. It holds within it a potential for discovery that could redefine what we know about the building blocks of planets, moons, and perhaps even life itself. Haumea's dazzling, crystalline surface seems to challenge the natural order of time and entropy. In the cold vacuum of space, where cosmic radiation should erode and darken its icy facade, Haumea instead reflects light with youthful brilliance. Could this defiance of natural decay hint at a subsurface reservoir of activity? Imagine geysers of water vapor or slush erupting from beneath its crust, driven by hidden heat sources deep within the dwarf planet. These cryovolcanic outbursts could not only refresh the surface but also eject material into space, replenishing its mysterious ring. The possibility of internal heating raises profound questions. If radioactive isotopes within Haumea's core are decaying, they could generate enough warmth to maintain a semi-liquid layer beneath the icy exterior. Alternatively, tidal forces exerted by its moons, particularly during periods of orbital resonance, might provide the necessary energy to melt portions of its interior. Such a scenario transforms Haumea from a frozen relic into a living world, where internal dynamics shape its surface and surrounding environment. But what if Haumea's heat is not entirely internal? The interactions between its surface and the vacuum of space could create unique thermodynamic phenomena. Sublimation, where ice transitions directly from a solid to a gas, might be occurring on Haumea's surface. If so, the escaping gas could carry fine particles with it, contributing to the material in its ring. Such a process would suggest that Haumea's ring is not merely a relic of the past but an active feature, evolving in real time. Observing changes in the ring's composition and density over decades could provide a rare glimpse into the ongoing processes shaping this distant world. Haumea's moons add layers of complexity to its system. Haumea, with its steady orbit and icy surface, appears calm and orderly, a stark contrast to Namaka's erratic path. Yet beneath this seeming tranquility, Haumea may hold secrets about Haumea's past. If its surface contains traces of materials not found on Haumea, it could indicate that the moon captured debris from other collisions or interactions in the Kuiper Belt. Meanwhile, Namaka's chaotic behavior suggests a history of gravitational disruptions. Its current orbit is a clue, a dynamic puzzle piece that, when understood, could reveal the violent forces that shaped this system billions of years ago. Haumea's enigmatic ring challenges the boundaries of our understanding of celestial mechanics. Unlike the dense, towering rings of Saturn or the faint arcs of Neptune, Haumea's ring exists in a fragile balance, held together by forces we are only beginning to comprehend. How did this ring form, and why has it persisted? Is it the result of a single catastrophic event, a piece of Haumea itself torn free by rotational forces? Or is it a dynamic feature, constantly fed by material ejected from Haumea's surface? If the latter is true, then Haumea could be in the process of reshaping its own environment, creating a system of rings and moons that evolves over time. And then there are the fragments, the scattered pieces of the Haumea family, drifting through the Kuiper Belt like whispers of a forgotten past. These icy bodies, with their shared spectral properties and orbital paths, are the remnants of a cosmic explosion. Studying them is like examining shards of ancient pottery, each fragment holding clues to the greater whole. Together, they paint a picture of Haumea's violent birth, revealing the forces that sculpted its unique shape and set it spinning at breakneck speed. But the family's existence raises even deeper questions. Was Haumea once part of an even larger body, perhaps a proto-dwarf planet that shattered in a series of collisions? If so, these fragments are more than debris. They are witnesses to the chaotic dance of formation that defines the Kuiper Belt. Haumea's story also forces us to consider the broader implications for planetary science. If such a dynamic, active world can exist in the cold outer reaches of our solar system, what does that say about the potential for similar worlds elsewhere? As we discover exoplanets orbiting other stars, many of them icy bodies in distant orbits, Haumea serves as a model for understanding their behavior. Its rapid spin, ring system, and moons offer a blueprint for interpreting the physical and chemical processes that shape exoplanets in similar environments. The Kuiper Belt itself becomes a stage for exploration, its icy worlds offering endless opportunities for discovery. Haumea is just one of many dwarf planets, each with its own unique features and mysteries. Together, these objects form a mosaic of the solar system's early history, preserving the conditions and materials that existed when the planets were young. By studying Haumea and its neighbors, we can piece together a narrative of how the outer solar system evolved, from the chaotic collisions of its infancy to the delicate balances of its present. As we look to the future, Haumea beckons as a target for exploration. A spacecraft mission to this distant world would be a monumental achievement, offering the chance to capture high-resolution images of its surface, ring, and moons. Instruments could probe its interior, searching for signs of liquid water or thermal activity. Sampling particles from its ring could reveal their composition and origin, providing direct evidence of the processes shaping Haumea today. Such a mission would not only answer long-standing questions but also open new avenues of inquiry, inspiring a deeper understanding of the Kuiper Belt and the solar system as a whole. Haumea spins on, a frozen sentinel on the edge of the solar system, carrying the secrets of its past while shaping its future. Its story is not just one of survival but of transformation, a tale of creation and destruction, of balance and chaos. As our technology advances and our curiosity deepens, Haumea promises to reveal its secrets, one enigmatic turn at a time. It is not merely a distant world. It is a challenge, an inspiration, and the universe is far more complex and beautiful than we ever imagined. Haumea spins relentlessly, a celestial anomaly that resists simplicity. It resides in the cold embrace of the Kuiper Belt, yet it burns brightly in the imaginations of astronomers, theorists, and dreamers alike. With every turn, it challenges our understanding of physics, chemistry, and the fragile balance of forces that govern the universe. Its shimmering surface, dynamic moons, and enigmatic ring system make it a beacon of intrigue. A frozen laboratory where the rules of the cosmos are laid bare, waiting to be deciphered. What makes Haumea extraordinary is not just its rapid spin or its elongated shape, but the intricate interplay of forces that hold it together. It's a world seemingly at odds with itself. The centrifugal forces acting upon it, driven by its breakneck rotation, work tirelessly to fling material outward, while its own gravity pulls inward, trying to maintain cohesion. This delicate balance creates a state of tension that has persisted for billions of years. But could this balance one day fail? If Haumea's rotation accelerates even slightly, or if external forces disturb its equilibrium, the dwarf planet could undergo a catastrophic event, shedding material into space and reshaping itself entirely. Such an event could provide a real-time glimpse into the processes that shaped not only Haumea but also countless other objects in the early solar system. It might offer answers to the origin of Haumea's existing ring, an icy halo that seems impossibly stable yet teems with questions. The particles in this ring are not random. They follow specific paths, locked into orbits that suggest a history of gravitational interactions and subtle dynamics. Could they hold the molecular fingerprints of Haumea's crust? Or perhaps even older material from the Kuiper Belt, predating Haumea itself? Each particle is a messenger from another time, a piece of cosmic history suspended in perpetual motion. The surface of Haumea, glimmering with crystalline water ice, seems almost alive in its defiance of entropy. Such ice should not exist in a region as cold and irradiated as the Kuiper Belt. Cosmic rays and ultraviolet radiation from distant stars should have rendered it amorphous long ago. And yet Haumea gleams. This raises profound questions about its internal activity. Could heat from its rocky core, perhaps generated by the slow decay of radioactive isotopes, be driving convection beneath its icy mantle? Such movement could bring fresh ice to the surface, constantly renewing its crystalline sheen. If this is the case, the implications are staggering. Haumea might not be the inert, frozen world it appears to be, but a dynamic body with ongoing geological processes. These processes might include cryovolcanism, where subsurface water or slush erupts through cracks in the crust, only to freeze instantly in the vacuum of space. Such eruptions could explain not only the crystalline nature of the surface but also the presence of the ring, as ejected material might accumulate in stable orbits around the dwarf planet. The moons of Haumea add another layer of complexity to this dynamic system. Haumea, the larger of the two, is a fascinating world in its own right. Its surface, rich in water ice, mirrors that of Haumea, suggesting a shared origin. But Haumea's near-circular orbit and apparent stability contrast sharply with Namaka, its smaller, more erratic sibling. Namaka's irregular path hints at past gravitational interactions, perhaps even orbital resonances with Haumea or disturbances caused by Haumea's rapid spin. These interactions may have generated tidal forces within Haumea, heating its interior and driving the processes that renew its surface. The history of Haumea's system is written in these moons, its ring, and the family of fragments scattered across the Kuiper belt. This family, a collection of icy bodies with spectral properties nearly identical to Haumea, represents the shattered remnants of a larger whole. They are not random objects but a coherent group, orbiting the sun in harmony as if paying homage to the collision that created them. Each fragment is a clue, a piece of the puzzle that scientists are painstakingly assembling. Together, they tell a story of violence, survival, and transformation. But what if Haumea's story is not unique? What if other worlds in the Kuiper belt or beyond share similar histories? As telescopes peer deeper into space, they are uncovering icy planets and moons in distant star systems, many of which bear striking resemblances to Haumea. These discoveries suggest that the processes that shaped Haumea are not isolated to our solar system but are part of a universal pattern. Haumea becomes a Rosetta Stone for understanding the behavior of icy bodies throughout the cosmos, a touchstone for studying the forces of collision, rotation, and gravitational interaction on a galactic scale. The potential for exploration of Haumea is boundless. A dedicated mission to this distant world could transform our understanding of icy bodies. Imagine a spacecraft equipped with advanced imaging systems, spectrometers, and even cryogenic sampling instruments, arriving in Haumea's orbit. It could map the dwarf planet's surface in exquisite detail, capturing the cracks, fissures, and potential cryovolcanic vents that hint at its internal processes. Probes could analyze the composition of its ring, unraveling its origins and evolution. And landers might even touch down on Haumea or one of its moons, drilling into the ice to search for signs of past or present activity. The implications of such a mission would extend far beyond Haumea itself. The data collected could redefine our models of planetary formation and evolution, offering insights that apply to icy moons like Europa and Enceladus, to distant exoplanets, and even to the earliest epochs of the solar system. Haumea, in its shimmering isolation, holds the potential to illuminate not just its own mysteries, but the mysteries of countless other worlds. For now, Haumea spins on, an icy enigma on the edge of our solar system, daring us to look closer. Its beauty is not just in its shimmering surface or its haunting ring, but in its complexity. A complexity that reminds us that the universe is full of surprises, waiting to be discovered. Haumea is more than a dwarf planet. It is a challenge, a wonder, and a beacon of curiosity, inviting us to unravel its secrets one discovery at a time. Haumea's enigmatic presence in the Kuiper belt is a testament to the resilience and complexity of celestial objects that dwell in the outermost reaches of our solar system. It is a cosmic storyteller, spinning tirelessly, whispering tales of ancient collisions, hidden internal processes, and an ever-evolving relationship with its surroundings. Each rotation, each icy glint off its surface, is a fragment of a larger narrative that invites us to explore deeper, ask more questions, and push the boundaries of what we know. The dwarf planet's unique shape is a direct consequence of its incredible rotation speed. A speed so fast it has distorted its body into an ellipsoid, far from the spherical equilibrium typically seen in celestial objects of its size. This deformation is a window into the physics of rotational dynamics under extreme conditions. Haumea's rapid spin stretches its mass outward, generating centrifugal forces that test the limits of its structural integrity. Scientists theorize that if Haumea were to spin even slightly faster, these forces might overcome its gravity, causing chunks of its surface to break away, forming additional debris or reshaping its ring system. Is Haumea already nearing this breaking point, or could it stabilize indefinitely in this precarious balance? The existence of Haumea's ring further complicates our understanding of how such features form and persist. Unlike the massive gas giants whose rings are sustained by vast gravitational wells and shepherd moons, Haumea's much smaller mass and rapid spin create a dynamic and delicate environment for its ring. Simulations of Haumea's ring dynamics suggest that the particles orbiting the dwarf planet are locked in a resonance with its rotation, stabilized by the very forces that seem poised to disrupt them. But the precise origin of these particles remains unclear. Were they ejected from Haumea's surface, torn free by its incredible spin? Or are they remnants of an ancient collision, preserved in this icy halo by some yet unknown mechanism? Haumea's moons, Hayaka and Namaka, act as gravitational counterpoints in this complex system. Hayaka, orbiting farther from Haumea, is relatively stable, but Namaka's erratic path suggests a history of significant gravitational interactions. This imbalance between the moons may have influenced the development of Haumea's ring, either by stabilizing its particles through subtle resonances or by contributing to the chaotic forces that prevent material from coalescing into additional moons. Together, these moons form a dynamic trio with Haumea, their motions a silent record of billions of years of orbital evolution. As scientists delve deeper into Haumea's mysteries, the crystalline water ice on its surface remains one of the most compelling puzzles. This ice, which glitters under the faint light of the sun, should not exist in the Kuiper Belt, where cosmic rays and ultraviolet radiation degrade crystalline structures over time. The persistence of this ice suggests ongoing resurfacing processes, likely driven by internal activity. But what mechanisms could keep Haumea geologically active in such a cold and distant region of the solar system? Radioactive decay within Haumea's rocky core is one possibility. Even small amounts of radioactive isotopes could produce enough heat to maintain a subsurface ocean or slushy layer beneath the ice. This internal warmth could drive convection currents, slowly cycling material to the surface and creating the cracks and fissures that might act as vents for cryovolcanism. Alternatively, tidal forces from its moons could generate enough friction within Haumea to keep parts of its interior warm. These processes, while speculative, paint a picture of a world that is far from static. A world where ice flows, cracks form, and energy moves in ways that defy the expectations of a frozen, isolated dwarf planet. The potential for a hidden ocean beneath Haumea's icy crust is particularly tantalizing. Subsurface oceans have been confirmed on moons like Europa and Enceladus, where they are thought to interact with rocky cores to create complex chemical environments. Could a similar ocean exist on Haumea, shielded from the cold vacuum of space by its icy shell? If so, it might contain the building blocks of life, formed in conditions entirely unlike those on Earth. Haumea's extreme distance from the Sun makes it an unlikely candidate for habitability in the traditional sense, but its internal chemistry could provide clues about the potential for life in other icy worlds, both in our solar system and beyond. Haumea's family of fragments scattered across the Kuiper Belt adds yet another layer to its story. These objects, sharing similar orbits and spectral properties, are the remnants of a massive collision that likely shaped Haumea's current form. By studying these fragments, astronomers hope to reconstruct the events of this ancient impact, its energy, its aftermath, and the processes that allowed Haumea to emerge as one of the fastest rotating objects of its kind. Each fragment is a time capsule, preserving information about the composition and conditions of the early solar system. Together, they form a mosaic that, when pieced together, reveals the violent, dynamic history of the Kuiper Belt. The implications of Haumea's study extend far beyond the Kuiper Belt. As telescopes detect more exoplanets, many of which are icy bodies in distant orbits around their stars, Haumea serves as a model for understanding these worlds. Its rapid spin, unusual shape, and complex system of moons and rings offer a template for interpreting the physical and chemical processes that might shape similar objects across the galaxy. Haumea's story is not just a local one. It is part of a universal narrative about the formation and evolution of planets and moons in icy environments. As humanity's technological reach grows, the prospect of exploring Haumea directly becomes increasingly feasible. A spacecraft mission to Haumea could revolutionize our understanding of icy worlds. Equipped with advanced imaging systems, spectrometers, and probes, such a mission could map Haumea's surface in unparalleled detail, analyze the composition of its ring and moons, and search for signs of subsurface activity. It could even deploy landers or robotic explorers to sample Haumea's surface ice, testing for organic compounds or other chemical signatures that might hint at its internal processes. Such a mission would not only answer existing questions about Haumea but also raise new ones, pushing the boundaries of planetary science. For now, Haumea remains a glittering mystery on the edge of the solar system, spinning ceaselessly, inviting us to uncover its secrets. Its rapid rotation, shimmering ice, and dynamic system of moons and rings are more than scientific curiosities. They are a reminder of the complexity and beauty of the universe. Haumea stands as a beacon of curiosity, a challenge to our understanding, and a testament to the unyielding forces that shape the cosmos. Its story is far from over, and as we continue to explore, it promises to reveal new chapters that will inspire wonder and discovery for generations to come. Haumea's story, spinning on the edges of the solar system, is a tale that transcends its icy surface and fragmented history. It is a symbol of how much there is left to discover in the vast expanse of space, where even the smallest celestial bodies can challenge the limits of human understanding. Its enigmatic features, a dazzling crystalline crust, a tenuous yet intricate ring, and moons that seem to dance to the rhythm of its rotation, represent questions that stretch the imagination. Yet these are not questions meant to linger unanswered. They are a call to action, urging us to reach farther and think deeper. As we look at Haumea, shimmering against the darkness of the Kuiper Belt, we see not just a world but a gateway. It is a bridge between the past and the future, between the solar system's earliest moments and the technologies we have yet to invent. Each rotation carries the echoes of a violent birth, the scars of ancient impacts, and the whispers of processes still unfolding. It's not just a frozen body but a living archive, holding secrets that span billions of years. To unravel those secrets is to understand not just Haumea but the forces that have shaped every world, including our own. Imagine the day a spacecraft finally reaches Haumea, slipping into orbit to become the first emissary from Earth to this icy realm. Cameras would capture its elongated shape in breathtaking detail, revealing the fractures and ridges of its surface, the glittering complexities of its ring, and the textures of its moons. Instruments would analyze the ice for signs of molecular diversity, searching for the fingerprints of the processes that renew its surface. A lander might touch down, drilling into the frozen crust to uncover ancient materials preserved from the dawn of the solar system. Each piece of data sent back to Earth would deepen our understanding, not just of Haumea, but of the outer solar system and the origins of planetary systems everywhere. And what if Haumea's secrets lead to discoveries that redefine what we know about life? Subsurface oceans hidden beneath kilometers of ice could harbor chemical processes akin to those that gave rise to life on Earth. The ring particles, studied closely, might reveal unexpected organic compounds, raising questions about the prevalence of prebiotic chemistry in the outer solar system. Haumea, seemingly distant and cold, could be the key to understanding how the conditions for life emerge in the most unlikely places. But even beyond the science, Haumea inspires something more profound: wonder. It reminds us that the universe is far from static or simple. Even in the most remote corners, there is activity, change, and evolution. Haumea is a story of resilience, a world forged in the chaos of collisions, yet still spinning with purpose. It is a testament to the idea that every object in the cosmos, no matter how small or far away, plays a role in the greater narrative of existence. Haumea's ending is not final. It is open, spinning endlessly like its rapid rotation. It is an invitation to keep exploring, to send missions, build telescopes, and push the boundaries of what humanity can achieve. It is a reminder that the edge of the solar system is not the edge of knowledge, but the beginning of new frontiers. Haumea spins, its secrets locked in ice and orbit, waiting for the day we finally uncover them. Its story will not end with mystery. It will end with discovery, with answers that inspire even more profound questions, and with a deeper understanding of the universe and our place within it.